Your hand, if you look at it now in whatever light you have around you, is made of a single bone running from your shoulder to your elbow, two bones running from your elbow to your wrist, a cluster of small bones forming the wrist itself, and 5 slender rays that fan outward into the fingers at its end. That arrangement, 1, then 2, then many, then 5, was already present 375 million years ago in the pectoral fin of a fish that lived in the shallow tropical streams of what is now the Canadian Arctic. The animal had scales and gills and a body that worked in water, and it swam. And inside the fin, it used to push itself along the bottom of a river. The hand you are holding in front of you right now was already, in a rough and unfinished way, starting to take shape. That sentence is not a metaphor. In the year 2020, a team of paleontologists led by Richard Cloutier in Quebec passed a complete specimen of another lobe-finned fish, Elpistostege watsoni, a creature longer than a grown man that lived about 380 million years ago, through a high-energy CT scanner. For most of the 20th century, Elpistostege had been known only from a piece of a skull. This time there was a whole body, and the scan was aimed at the inside of the fin, beneath the scales and the compacted sediment, beneath the lepidotrichia, the thin, bony rays that hold a fish's fin open in the water. What came back on the screen, nested between the wrist-like bones and the fin rays, was a row of small articulated elements arranged in columns. 2 unmistakable columns, 3 more strongly suggested. Finger bones, inside a fin, in a fish that had never once in its life hauled itself onto a shore. The hand was there before there was any land to reach for. This is the long story underneath that small sentence. The uneven, mostly underwater story of how a lineage of fish came to carry the first draft of what is now your body, and what happened to that body when pressure and time and the slow sorting of variants moved it into a kind of life no vertebrate had ever lived before. Most of what you have probably heard about it is a single clean image, a determined fish gulping air, heaving itself up onto a muddy shore to claim the land for its descendants. It is a wonderful image. It is almost entirely the wrong image. The fish did not claim anything. The fish wanted nothing, because wanting requires a mind, and the animal whose fin was slowly becoming your hand did not know its fin was becoming anything at all. It was hunting in shallow water. It was staying out of the way of things larger than itself. It was looking from beneath the surface at the occasional shadow of something worth eating passing overhead. What it was doing, its ancestors had been doing for 100 million years. What its descendants would eventually do, walk, stand upright, speak in full sentences, listen to a voice describe all of this in the quiet of a late evening, was not yet even a possibility on the planet. The land, in the late Devonian period when this animal lived, was only beginning to hold its first true forests, and no vertebrate had made a home there yet. The whole world above the waterline was quieter than you can easily picture. There were insects and a low wind through the early ferns, and otherwise almost nothing. Every sound that would come later, every bird call, every frog, every wolf, every human voice, was still folded up inside the bodies of animals in the water, waiting for a reason to exist that had not yet arrived. Before any of this begins to open up, one small thing. If what you hear tonight feels worth being made, the subscribe button on a channel like this one does more for it than almost anything else. And in the comments, I would like to know something, not about the science, but about you. When you turn your hand over in front of you and consider the idea that this hand was, in its earliest version, already inside the fin of a Devonian fish, does that feel strange to you, or does it feel in some quiet way oddly familiar? I read the answers, and I find the question more interesting than almost anything I could tell you about it myself. Now, if you are comfortable, let yourself be a little more comfortable. Your jaw is probably tighter than it needs to be. The breath will lengthen on its own over the next little while, and you do not have to help it. The story begins not on land, but in a shallow, warm river in what is now the tropics of a vanished continent, under a sun you would not quite recognize, in a world where the trees were still young and the water was full of things that could kill you. In the shallow waters of the late Devonian, the amount of oxygen a fish could extract from the water was, for much of the year, not quite enough. Warm water holds less oxygen than cold water does, and these rivers were warm. The seasons rose and fell, ponds opened and closed, and the water itself was slowly becoming richer in a new kind of decomposing matter, fallen leaves, stems, roots, the debris of an emerging ecology on the shore, which fed bacteria and, as it rotted, drew down whatever dissolved oxygen remained. For a fish making a living in these shallows, the single most useful thing it could carry in its body was any form of supplement to what its gills were bringing in. This was the world of roughly 380 million years ago on a continent that no modern map will show you. It was called Laurussia, and it sat across the equator in a position we might now recognize as lying somewhere between the Amazon basin and Central Africa. The coastline you would be walking, if you could walk it, is today the Canadian Arctic. The climate was subtropical, humid, heavy with afternoon rainstorms, and the land, while not empty, was extraordinarily quiet. Above the waterline there were no birds, no frogs, no mammals, and none of the flying insects whose wings you are used to hearing on a summer evening. The first small wingless insects, springtails, among the earliest arthropods to make a home on land, lived there in the ground cover, but they produced almost no sound you could register. The first true forests were rising, built around an early tree called Archaeopteris that had real wood and could reach roughly 30 meters in height, and in the lower growth there were ferns and horsetails and early lycophytes. These trees shed their branches like the first drafts of autumn. The wind moved through them, and the rain fell through them, and otherwise the land held nothing that could interrupt the sound of its own weather. Every voice that would later fill that space, every bird call, every frog, every wolf, every human word, was still folded up inside animals that had not yet evolved. The silence of the Devonian land is not a romantic image. It is an accurate one. The water was an entirely different situation. The seas and the deeper rivers held so many fish of so many kinds that paleontologists sometimes call the whole period the Age of Fishes, and the name has not had much competition. The open water was ruled by armored predators called placoderms, fish with bony plates for faces and jaws that sharpened themselves as they closed. The largest of them, Dunkleosteus terrelli, reached up to about 8 meters in length, with a skull more than a meter across, and its bite is one of the few Devonian facts that survives even in the memory of people who have never heard the word Devonian. Sharks were present in the water as well, though smaller than they would become. Bony fish of every sort were diversifying, and in a quieter register, alongside all of this, swam the lobe-finned fish. The lobe-finned fish, the Sarcopterygians, whose name means fleshy-finned, were not built like the fish most people picture when they hear the word. Their paired fins were thick and muscular, attached to the body through a real joint and supported internally by articulated bones rather than held open by thin rays alone. The coelacanth, still alive today in the deep waters off southern Africa and Indonesia, is one of the last surviving members of their lineage. In the late Devonian, the lobe-finned fish were successful, diverse, and in many places numerous. Many were large, many were predators themselves, and many had occupied a particular ecological position. They lived in the shallows, hunting other fish and anything else that moved in water a meter deep or less. The shallows were a complicated place to live. They were a refuge from the biggest open water predators, which needed more room than the shallows could offer. They were richer in food because sunlight reached the bottom and everything downstream of sunlight grew faster there. But they were also the first water to warm, the first to stagnate, the first to lose oxygen when the organic matter piled up, and the first to disappear entirely when a dry season came through harder than usual. A lobe-finned fish in the shallows was exchanging one kind of danger for another. What it needed to stay was a way to keep breathing when the water could no longer fully oblige. Many of them already had one. The bony fish of the Devonian, including the lobe-finned group, carried in their bodies a simple paired sac connected by a tube to the gut, which they used when the water ran low to gulp air at the surface. This organ is the lung. It is not a tetrapod invention. It was already in the water, in some early form, tens of millions of years before any vertebrate set foot on a shore. In some descendants, the lung would stay a lung. In others, the ray-finned fish that make up most of the fish you know today, it would eventually be modified into a swim bladder, used for buoyancy rather than breathing. But in the Devonian shallows, the primary use was straightforward. A fish rose to the surface, took a swallow of air, and sent the oxygen into its blood directly through a soft, vascularized pocket in its own chest cavity. Here, quietly, one of the harder facts of this whole story begins to surface. The oxygen these fish were gulping, the oxygen in the air above their heads, was itself a byproduct. It had not been placed there for the benefit of any animal. Oxygen in the Earth's atmosphere is the waste gas of photosynthesis, produced by plants and bacteria as a leftover of the reactions that feed them, and it had been accumulating in the sky for more than 2 billion years before any fish considered the idea of breathing it. During the Devonian specifically, the level in the air was climbing sharply, in part because the new forests were spreading, and the new forests were very good at what they did. No one arranged this. No one decided the sky should become breathable, and no one decided there should be more oxygen for later animals to come along and find. The trees were running their own metabolism, and a lineage of fish in the warm, shallow water happened to be in a position to inherit the surplus. If you want to feel how close this world still is to you, consider what your own body did when you were about 4 weeks along, as an embryo not much larger than a grain of rice. At that stage, every human being develops a series of ridges along the sides of the neck, 4 of them, arranged one behind the other. They are called pharyngeal arches, and in a fish embryo they become the gills. In you, they do not. Most are reabsorbed before birth, quietly, without any trace anyone would later notice. The ones that remain become the bones of your jaw, the small bones of your middle ear, your hyoid, your larynx, and the muscles that let you chew and swallow and shape words. The voice you are listening to right now is produced in part by structures that in a fish would be breathing water. One fish in a shallow, warm river somewhere on this vanished continent will do for a picture of the rest. Not a strange fish, not a creature in the middle of becoming something different. A late Devonian lobe-finned fish of a common kind, going about its kind of life with no sense of being in the middle of anything. Its name, from the rocks in which it was first described in the 19th century, is Eusthenopteron. And whatever it was doing on a given afternoon, it was not thinking about the land. Picture it in a slow, green river in mid-afternoon at a depth of perhaps a meter. The sun is overhead, and the water holds that particular quality of light you sometimes see in shallow tropical rivers today, where the surface acts as a ceiling and the sediment on the bottom throws back a soft brown glow. The fish is about a meter long, dark-scaled along the back, paler underneath. Its head is somewhat pointed. Its eyes are ordinary fish eyes set on the sides of the skull. Its body has the smooth, muscular curve of a predator that moves through water by bending itself. From a distance, anyone would recognize it as a fish, and the recognition would be correct. Its name, assigned more than a century ago from a fossil first described in Canadian shales, is Eusthenopteron fordi. It belonged to a group within the lobe-finned lineage called the Tristicopterids, and it was common, successful, and in no particular hurry. What made it a little unusual, from the point of view of any fish you have seen recently at a market, was the construction of its paired fins. The ones on its sides, the pectoral fins set behind the gills, were not thin sheets held open by bony rays. They had those rays at the edges like any fish, but set back at the base of each fin was a stubby, fleshy lobe. Inside that lobe, hidden under the scales, were bones. A single bone lay closest to the body, the same bone that in your own arm runs from the shoulder to the elbow. It is called the humerus. Beyond it, articulating at a kind of elbow joint, were two parallel bones of roughly equal length. You have them too, in your forearm. They are called the radius and the ulna. This is not a resemblance. It is an inheritance. The humerus in Eusthenopteron, the humerus in a frog, the humerus in a pigeon, the humerus in a horse, and the humerus presently resting against whatever your back is resting against, these are all the same bone. Not similar, the same. The name was given, originally, because the bones looked alike across groups of animals that otherwise looked nothing alike, and as soon as the science of evolution was available, the reason came clear. They are the same bone because they all descend, through an unbroken line of generations, from the one bone then two bones arrangement that was already in place in the fins of a fish like this one 385 million years ago. What the fish was using it for was not walking, it was pushing against the bottom of the river, against submerged logs, against the root tangles of the early ferns along the bank. A lobe-finned predator of this size, in water this shallow, could not rely on open water swimming alone. Much of its daily hunting took place in places where there was almost no room to swim, and where the only way to get through was to brace itself with those stiff, muscular fins and lever its body forward. The fin acted as a combination of paddle, prop, and anchor. It was also, occasionally, a brake. When Eusthenopteron wanted to hold its position in a current while it waited for something edible to drift past, it could dig the stubby fins into the gravel and simply remain there, stationary, for as long as patience asked. None of this was unusual for its time. Several other lineages of lobe-finned fish were doing variations of the same thing, in similar habitats, all across what were then the warm, shallow margins of Laurussia. And none of this, not one instant of it, was being done with any eye to what would come later. Eusthenopteron was not beginning a journey. Eusthenopteron was an entirely finished, self-consistent, late Devonian fish whose body plan had arrived at a workable version of a particular life and was getting on with living it. It fed, it bred, it avoided larger predators, and when it could not avoid them, it was eaten. The humerus in its fin was not a prototype of anything. It was a humerus, doing the work a humerus does in a fish that needs to push against things. The temptation here, for anyone telling this story, is almost impossible to resist. The temptation is to say that Eusthenopteron's fins were already reaching toward the future, that the elbow was already forming, the forearm already present, the wrist already implied, and that the lineage was somehow, in some quiet way, leaning in the direction of land. This is the single most common mistake in the popular telling of evolution, and it is worth being careful about it because it gets the causality exactly backwards. The fins were not pre-versions of limbs. They were fully functional fins, shaped by millions of years of selection for doing fin things well in shallow water. The fact that a very small subset of the lineage, tens of millions of years later, would end up in bodies that used related bones for walking is a fact about the future, not about Eusthenopteron. The animal in the river was not heading anywhere. It was where it was. This distinction matters because the word we reach for, adaptation, carries with it an accidental suggestion of intent. It sounds as if something was adapted for a purpose. Nothing in natural selection has a purpose in that sense. What happens is narrower and, once you see it, stranger. Individuals in a population vary. Some of that variation is heritable. The individuals whose variations let them survive long enough and reproduce often enough pass their variations along more reliably than the ones who do not. Over many generations, the average body in the population shifts very slowly toward the variations that worked. No one is pushing anything forward. The variations that failed simply left fewer descendants, and the variations that worked simply left more, and the difference compounds. What looks, from a distance, like an adapted design is the statistical residue of everything else having died. For the fish in the river, the practical consequence of this was invisible. A given Eusthenopteron was born with whatever fins its parents could give it, hunted with them, pushed through the reeds with them, caught what it could catch, and in due course produced young or did not. If its fins were slightly more muscular than average, and the shallow water happened to be harder to navigate that particular decade, it might feed a little better and produce a few more surviving young than its cousins. Nothing about this felt, to the fish, like progress. It did not feel like anything. The shift in the average fin shape of the population across 10,000 generations is entirely invisible inside any single life. It is a statistic produced by deaths. If you want to touch the part of this that still belongs to you, bend your arm. Feel where the elbow is. Notice how the forearm, below the joint, contains two bones rather than one. You can feel them if you grip your forearm with your other hand and rotate the wrist. The two bones are the radius and the ulna. They separate and cross as you rotate, which is why the rotation is possible at all. This arrangement is the reason you can turn a doorknob, hold a cup, wave, write, and perform almost every fine motor act your species has come to depend on. And it is the same arrangement, with the same names, that was present in the fin of a fish in the shallows of a vanished continent, being used in that river to push against a log. The thing is not that your arm is like Eusthenopteron's fin. The thing is that your arm is Eusthenopteron's fin, altered over an unbroken chain of generations and put to a new use. Nothing new was invented for you. The pieces were all already there, in the water, doing something else, long before there was any shore to reach for. And when the shore eventually did enter the story of this lineage, it entered not as a destination, but as an unexpected consequence of structures that had already been in place for reasons of their own for millions of years. The fish in the river has no idea any of this is happening. It is, at this particular moment, holding itself in place against a current, fin dug into the gravel, waiting for something to move. There is a particular kind of scientific confidence that makes almost no sense from the outside. It is the confidence that a specific fossil of a specific animal of a specific age exists somewhere in the world, and that if you look in the right place, you will find it. It is not a confidence about what has been discovered. It is a confidence about what has not yet been discovered, and cannot be guaranteed to exist, and might simply not have survived the last 375 million years at all. To an outsider, it can look like arrogance, or like a particularly expensive kind of wishful thinking. To someone inside the practice, it is something closer to a logical necessity. 2 points on a line imply a third point between them. If you are confident enough about the 2 points, you go and look for the third. By the late 1990s, the 2 points were visible, and the gap between them was conspicuous. On one side stood Eusthenopteron and its relatives, the lobe-finned fish of the Middle and Late Devonian, fully aquatic, with paired fins, carrying the humerus radius ulnar arrangement buried inside muscular lobes. On the other side stood the early tetrapods, Acanthostega and Elpistostege, known since the 1930s from East Greenland and refined by the work of Jennifer Clack at Cambridge through the 1980s and 1990s. These were four-limbed animals with recognizable feet, ribs strong enough to suggest some weight-bearing, and skulls unmistakably different from the skulls of the lobe-finned fish on the other side of the gap. The fish lineages ran up to about 380 million years ago. The earliest tetrapods arrived by about 365 million years ago. Between them lay roughly 15 million years of evolutionary history, with no meaningful fossils in it. Not none, fragments, jaw pieces, scattered material, but nothing coherent enough to show what the body actually looked like while it was changing. 15 million years is longer than our entire lineage has existed as recognizable humans. It is plenty of time, in other words, for a great deal to happen, and a great deal had evidently happened. The question was where to find it. The answer turned on three conditions, which Ted Deichler at the Academy of Natural Sciences in Philadelphia and Neil Shubin, then moving to the University of Chicago, had worked out for themselves over the previous decade. To find fossils of a particular age, you need rocks of that age. To find fossils at all, you need rocks of the right kind, typically sedimentary rocks formed in the right depositional environment, which for their purposes meant the beds of shallow tropical streams. And to find anything without spending a lifetime digging, you need those rocks to be exposed on the surface, somewhere that erosion has already done most of the work of uncovering them. The global map of places where all three conditions meet for the relevant interval of the Devonian is surprisingly small. Most of it had already been worked. The Devonian outcrops of the eastern United States, particularly Pennsylvania, had been picked over for generations, partly by Deichler himself along highway road cuts. The Greenland sites had produced Acanthostega and Elpistostege. The Baltic region had produced Panderichthys. There was one place left on the map, as far as they could tell, where rocks of the right age and the right type sat exposed in quantity and had never been searched for vertebrate fossils. It was marked, in the undergraduate geology textbook they were consulting, as a long band stretching across the Canadian Arctic archipelago on an island called Ellesmere. Ellesmere Island lies at about 80 degrees north latitude, roughly 600 miles south of the North Pole. It is accessible in the summer, barely, by a small plain route that ends on unprepared tundra. The weather during the working months ranges from cold rain to snow, and the season is short, roughly 6 to 8 weeks of workable conditions a year, during which the sun does not set. The surrounding wildlife includes polar bears, which means that every field party has to include someone armed, and that someone has to stay awake while the others dig. The logistics are expensive enough that a single field season runs into 6 figures, and an unsuccessful season means a significant fraction of a research budget has gone to producing nothing. Deichler and Shubin first went there in 1999. The first season produced little. The second, in 2000, produced fragments of fishbone, the right general kind, enough to suggest that the rocks held something, but nothing coherent enough to argue from. The third season, in 2002, turned up a single promising fragment of a flat, pointed snout, the sort of snout that hinted at the general territory they were looking for without resolving what it belonged to. The fourth, in 2003, yielded more of the same. By that point, they had been going to Ellesmere for 4 summers. Each season had cost roughly $100,000. Their funders were patient, but not endlessly patient, and the informal understanding heading into the 5th year was that 2004 would be the last fully supported expedition. If it did not produce the animal, the project in its present form was probably over. They returned in July of 2004. The crew that year included Shubin, Deichler, Farish Jenkins from Harvard, Steve Gatesy from Brown, the graduate students who had been working the quarry in previous years, and a logistics team. The quarry itself was a rust-coloured exposure in the Fram Formation, a stretch of ancient stream deposits that had, 375 million years earlier, lain on the equator. They had known the rock was right. What they did not yet know was whether there was anything in it. What Shubin describes, in his own accounts, is a scene that sounds almost absurd when you try to put it into sentences. He was working at the bottom of the quarry, breaking ice more often than rock, because the summer in that latitude is not warm enough to clear overnight frost from the working faces. At some point during that day, he cracked a section of ice away and saw, underneath it, a patch of scales, unlike anything else they had found in that quarry in 5 years. The pattern was slightly wrong, not the pattern of the fish they already knew from the site. He followed the scales into the rock, carefully, because anything that fragile has to be followed rather than excavated, and within a short distance he reached what turned out to be a set of jaws. The jaws were also wrong. They were not the jaws of any of the lobe-finned fish that anyone on the crew had ever seen. They looked, in their own narrow way, as if they might have been attached to a flat head. Shortly afterward, Steve Gatesy, working another section of the same quarry, noticed the tip of a snout peering out of a cleared face. It looked flat. They enclosed both specimens in plaster jackets, the standard protective shell used to transport delicate fossils out of the field, loaded them onto helicopters, and sent them south to be prepared in laboratories at the Academy of Natural Sciences in Philadelphia and the University of Chicago. Over the following months, fossil preparators removed the surrounding rock grain by grain, and what emerged was an articulated front half of an animal a little over 2 meters long, with scales like a fish, fins like a fish, gills like a fish, and a short list of features that were not like a fish at all. The 2 papers describing it were published in the journal Nature on the 6th of April 2006. The name of the animal, chosen after the team consulted the Council of Elders of Nunavut, the territory in which Ellesmere Island lies, was Tiktaalik rosea. The word is from Inuktitut, the language of the Inuit of the region, and it means, roughly, a large freshwater fish seen in the shallows. When Jennifer Clack, whose own work on Acanthostega had helped define the gap the prediction was aimed at, was asked about Tiktaalik, she said something along the lines of pointing at it and saying that it was exactly what everyone had been saying should exist. The prediction had worked. The third point on the line had been there all along. A thing worth pausing on before we look at the animal itself is what this kind of success actually means. The temptation is to call it a triumph of theory, and in a certain narrow sense that is right. Evolution as a framework made a real prediction, a transitional form of roughly this kind, in rocks of roughly this age, in a setting of roughly this sort, and the prediction held. But the triumph is not that anyone had the idea. The triumph is that the rocks cooperated. There was no guarantee that the right animal had been preserved, or that what had been preserved was exposed at the surface, or that the working face in the quarry on that particular July afternoon contained anything at all. The prediction was a real one in the sense that it could have failed honestly, and it almost did, across 4 seasons of finding not quite enough. This is worth holding on to as the story continues, because what comes next, the animal itself, with its flat head and its mobile neck and its curious fins, is often told in a way that makes it sound inevitable. It was not inevitable. It was a fish that lived for a few million years in a particular stretch of ancient river and died in the ordinary way and was buried in sediment of a kind that happens to preserve bones well, and survived 375 million years of geological rearrangement and was lifted to the surface by the erosion of a high Arctic landscape and lay there in a rust-coloured cliff face waiting for someone to crack the right piece of ice off it in July of 2004. Every link in that chain could have failed. None of them did. What the prediction supplied was the willingness to keep going back for a fifth summer. What the rocks supplied was the animal. If you want a quiet place to set this against your own body for a moment, not the hand this time but something smaller, touch the soft patch of skin just in front of your ear at the top of the jaw. Somewhere between 1 and 10% of people, depending on how studies count it, have a small pit or dimple there, sometimes so shallow it is almost invisible. It is called a preauricular sinus. It is a leftover of the incomplete fusion of the same embryonic structures that, in a fish, form the second gill arch, and the passage water flows through between the gills and the skin. It has no function now. It is a small opening in the side of the human head that is there because the human embryo goes on remembering something about being a fish long enough for occasional errors of closure to survive into adulthood. Most people's pits close. Some do not. The ones that do not are a minor cosmetic oddity, occasionally prone to infection and otherwise meaningless. Except that it is the gill slit of an animal that has been dead for 375 million years, carried intact inside the skulls of roughly 1 in 10 humans alive today, doing nothing. It was not preserved for any purpose. It was not kept on purpose at all. It is simply that nothing ever selected hard enough against its occasional persistence to finish removing it, and so it remained, a small dimple of the water world, still open on the side of a mammal's face. That is the shape of the fossil record seen from the inside. The prediction that led to Tiktaalik was aimed at the same kind of residue, written in stone instead of skin. The science worked because the traces were there to be found. And the traces were there to be found because selection, in general, does not clean up after itself. It preserves what works, it lets the rest drift and break and occasionally survive. The animal they pulled out of the ice in 2004 is, by every reasonable measure, one of the finest pieces of such residue ever recovered. The animal was about 2.5 meters long, though the largest individuals appear to have reached closer to 2 3/4 meters. That is roughly the length of a modern alligator. The body was heavy-scaled, flattened from top to bottom rather than side to side, and shaped in a way that no fish alive today will quite prepare you for. If you imagine a crocodile, and then imagine that the crocodile is a fish, with gills, with fins instead of feet, with a proper tail, you will be closer to the right silhouette than most other starting points can get you. The head was broad and triangular, ending in a long, low snout. The eyes sat on top of the skull, not on the sides where a fish's eyes usually sit, looking directly upward through the water at whatever passed overhead. The teeth inside the jaws were sharp. The body tapered into a single-lobed tail. By every ordinary measure, this was a fish. And yet, looking at the reconstructed skeleton, almost nothing about it lines up with the fish you know. The first thing that looks different is the head itself. In most fish, the back of the skull is fused directly to the shoulder girdle, so that when the body turns, the head turns with it. A fish cannot look around the way you can. It has to turn its whole body in the direction of whatever has caught its attention. In Tiktaalik, the bones that normally make this fusion, called the opercular series, and a set of smaller elements behind them, are absent or reduced. The skull has become detached from the shoulder. Between them, filling the space where those bones used to sit, there is a short, flexible region of vertebrae. What that short, flexible region makes possible is a motion that fish simply do not perform. The head can turn. Not far in Tiktaalik's case, nothing like the rotation you can do at your own neck, but enough to lift the snout toward the surface without the rest of the body having to follow. This small structural change is the first neck anywhere in the history of vertebrates that behaves the way a neck is supposed to behave. It is worth pausing on what that means in the water. If your eyes are on top of your head and you want to see what is moving on the surface, you have either to tilt your whole body or to tilt your head. Tilting the whole body is expensive. It takes muscle, it disturbs the water, and it announces your position to anything watching. Tilting the head alone is cheap. It is almost silent. For an ambush predator lying in the shallows, waiting under the cover of bankside vegetation for something to blunder into range, being able to track movement with just a turn of the skull is an enormous practical advantage. It is not an advantage that required the animal to leave the water. It was an advantage in water. The neck arrived first, and only later, much later, in lineages that descended from things like Tiktaalik, did it turn out to be equally useful for an animal lifting its head above the ground. The second thing that looks different is the pair of fins behind the gills. These are the pectoral fins, and they are where the prediction the Discovery team had been making across 4 unsuccessful seasons finally paid out. From the outside, the fin looks fishy. It has the broad, leaf-shaped outline of any lobe-finned fish's pectoral, and its edges are fringed with lepidotrichia, the thin, branching, bony rays that hold the fin open in water. But the inside, revealed once the preparators had worked through the surrounding rock, is not the interior of a fin that any earlier animal had been known to carry. The single bone at the base is a recognizable humerus, larger and heavier than eusthenopterons, with muscle attachment points that indicate considerable power. Past it, articulating at an elbow, sit the radius and the ulna, the same 2 parallel bones you can feel in your own forearm. Beyond them, where in a typical fish there would be a continuous sheet of small radials flowing out into the fin rays, Tiktaalik has something different again. It has a wrist. Not a fully articulated wrist of the kind a mammal carries, but a cluster of distinct, block-like bones that sit in a recognizable arrangement at the end of the forearm and allow the distal part of the fin to bend. Within the wrist, one can identify 2 specific elements, called the intermedium and the ulnare, that correspond, bone for bone, to wrist bones in every 4-limbed vertebrate that has lived since. Beyond the wrist, the fin continues out into rays, ending in fringed lepidotrichia rather than fingers. It is not a hand. It is, however, a fin with a joint inside it that behaves like the joint inside an arm. The practical use of this, like the neck, had nothing to do with walking on land. What the arrangement did, mechanically, was let Tiktaalik prop itself up on the bottom of a stream. The heavy humerus provided the power. The elbow allowed the fin to bend backward against the substrate. The wrist allowed the distal part of the fin to press flat against mud or gravel, distributing the animal's weight across a broader surface rather than concentrating it at a single point. An animal with fins of this kind in water shallow enough that its belly occasionally touched the bottom could hold itself in a half-crouch, head tilted up, eyes scanning the surface, body stabilized by 4 contact points against the ground. It is a hunting posture, not a locomotor one. It is the posture of an ambush predator that needs to keep still for long periods in variable current, in water too shallow for full swimming and too full of cover for any other approach to work. In 1996, Jennifer Clack had proposed that the limbs of the earliest tetrapods evolved initially for use in water rather than on land. Tiktaalik, a decade later, handed that proposal a striking piece of support. The skeleton in the Fram Formation was not an animal caught in the act of learning to walk. It was an animal whose fins had been reorganized quietly across millions of years for a highly specific job in shallow water, and whose body happened to carry, as a consequence of that reorganization, almost every one of the structural innovations that later tetrapods would put to use for an entirely different purpose. The mobile neck, the weight-bearing forelimb, the flattened skull, the eyes on top, and, as the team would eventually announce 8 years later, in 2014, based on a second block of material that had been sitting unprepared in storage, a pelvis larger and more robust than anyone had expected, with a deep hip socket suggesting that the hind fins were doing real propulsive work as well. In other words, a body in which both pairs of appendages were already contributing to the kind of four-point locomotion that the later tetrapods would inherit and refine. And yet, this is the part that is worth holding on to, Tiktaalik was not a tetrapod. It was not even particularly close to being a tetrapod in any functional sense. It had gills, it had fin rays, it had scales of a thoroughly fishy type overlapping in a diagonal pattern that would have made its flanks shine silver if you had seen it alive. It almost certainly could not have lived for any significant period out of water. Its lungs, which its ancestors had already possessed, would have helped it survive stagnant or oxygen-poor shallows, and its fins could have propped it briefly on the edge of a mudflat if it needed to push itself back into deeper water after being stranded. But the idea, sometimes suggested in popular accounts, that Tiktaalik was in any real sense a land animal or an amphibian or a creature that spent much of its time out of water, is not supported by the anatomy. Tiktaalik was a fish. It was a fish with an unusual body, shaped by an unusual habitat, carrying a set of structures that would later prove useful for something its own lineage was not doing. That it happens to sit in the cladogram, right next to the branch that gave rise to the first tetrapods, does not change what it was in its own life. It lived in the water. It died in the water. It was buried in a stream bed. The story of land, for its descendants, would continue without it. This is where the shape of the thing actually begins to come clear, because the story is not quite what the popular image suggests. Tiktaalik is not the first step onto land. Tiktaalik is evidence that the pieces which later made stepping onto land possible were already assembled, for their own reasons, in a fully aquatic body. The sequence did not run water, shallow water, land in clean succession. It ran through a long, patient period of rearrangement inside the water, neck before walking, elbow before walking, wrist before walking, weight-bearing hip before walking, during which no one involved was leaving the river. Only later, long after Tiktaalik's own kind had come and gone, would some descendants take the same pieces and start using them for something the original owners had never needed to do. There is a moment in this story that is worth offering honestly rather than smoothing over. We do not know with certainty whether Tiktaalik ever left the water at all. The discoverers have been careful about this from the beginning. Their stated view since 2006 has been that the animal was specialized for life in shallow streams, swampy habitats and ponds, and that it may have pulled itself up onto the shore for short periods. May have is not did. The fin, even with its wrist, still had fin rays at its tip rather than digits, and the body was still heavy enough that extended time out of water would have been a significant challenge. Some of what Tiktaalik could and could not do in air remains an open question. What the fossil tells us clearly is what its body had become. What it used that body for in detail from one afternoon to the next, it no longer has any way of saying. If you want a small place in your own body where this particular chapter's anatomy still lives, do one thing for me. Turn your head slowly to the left, as far as it comfortably goes, and then back. You did that without moving your shoulders. Your skull rotated on the first vertebra of your spine, a ring-shaped bone called the atlas, without the rest of your body having to follow. A fish cannot do what you just did. Eusthenopteron could not do what you just did. The first vertebrate in the history of the planet to be able to do something like it was a lineage of lobe-finned fish, of which Tiktaalik is the clearest preserved example, whose skulls came free of their shoulder girdles because their ambush hunting style rewarded small turns of the head against still water. The movement you just performed, the casual swivel of the head on the neck, is roughly 375 million years old, and it entered the world not because any animal decided it would be useful for looking around a room, but because a fish in a shallow stream needed to track a shadow at the surface without moving its body. The fish did not know it was doing this. It was only waiting, fins dug in, head angled slightly upward for whatever was going to move next. There is a quiet danger in telling an evolutionary story through a single beautifully preserved fossil, and it is worth naming clearly. The danger is that the single fossil starts to stand in for everything. Tiktaalik is a wonderful animal. It is also, in the popular telling, a little too wonderful. The fish that walked, the missing link, the one creature that crossed the threshold from water to land. None of that is accurate, and the inaccuracy matters because it obscures the shape of what was actually happening in the late Devonian. Tiktaalik was not alone. It was a member of a small group of lobe-finned fish scattered across what were then the tropical margins of several continents, and every one of them was, in its own way, working out some version of the same problem at the same time. The shallow waters of the Devonian were not empty, and they were not waiting for a protagonist. They were full of animals trying, in parallel, to make a living under a particular set of conditions, and several of those animals ended up with bodies that looked strikingly alike. The group is called the Elpistostegalians, after its type genus, an awkward word to pronounce out loud, which is partly why you rarely encounter it in the popular literature, and partly why Tiktaalik has done most of the public work of representing the whole group. An Elpistostegalian, in broad terms, is a lobe-finned fish with a flattened skull, eyes positioned near the top of the head, a reduced connection between the skull and the shoulder girdle, muscular pectoral fins with a recognizable internal arm skeleton, and a general ecological profile that suggests life in shallow, slow, warm water. 3 genera have been well enough preserved to tell us something coherent about their bodies. The first is Panderichthys, described from rocks in the Baltic region of what is now Latvia, about 380 million years old. The second is Tiktaalik itself, from Ellesmere Island, about 375 million years old. And the third, the one that has most recently changed the shape of the story, is Elpistostege watsoni, from the late Devonian rocks of Miguasha, in the Gaspé Peninsula of Quebec. Elpistostege had been known since 1938, when the British paleontologist Thomas Stanley Westall described a piece of a skull roof found at Miguasha and suggested, provisionally, that it might belong to an early amphibian. Another partial specimen turned up in the 1980s, and a third-party interpretation reclassified the animal as an advanced lobe-finned fish rather than a stem tetrapod. For most of the following decades, Elpistostege lived in the footnotes, a name in the phylogenies, a fragment in the collection, a placeholder for an animal we did not really know. That changed in 2010 when a nearly complete specimen, about 1.5 meters long, was excavated at the same Miguasha site. It was the first articulated body of the genus anyone had ever seen. The specimen ended up in the laboratory of Richard Cloutier at the Université du Québec à Rimouski, and over the next decade, a team led by Cloutier and the Australian paleontologist John Long, in collaboration with a number of colleagues, worked on a problem that the skull alone could not have answered. They wanted to see inside the fin. The outside of the fin was ordinary in the Elpistostegalian sense, lobed, scaled, fringed with bony rays. What mattered was the arrangement of the bones buried inside it, the internal skeleton, which in a compressed fossil is almost always inaccessible by traditional preparation. The ordinary method, for a fossil of this delicacy, would be to painstakingly remove the surrounding matrix grain by grain, a process that can take years and often damages the very structures you are trying to see. Cloutier's team used a different approach. They passed the specimen through a high-energy computed tomography scanner, essentially a very powerful medical CT adapted for dense mineral samples, and reconstructed the interior of the fin in 3 dimensions, bone by bone, without ever having to touch it physically. The reconstruction was published in the journal Nature in March of 2020, and it contained one result that no previous Elpistostegalian fossil had quite resolved. The pectoral fin of Elpistostege had, at its distal end, the end furthest from the body, a series of small articulated bones arranged in columns. 2 of the columns were unambiguous, consisting of multiple segments that lined up in the characteristic pattern of digit bones. 3 more columns were strongly suggested, though in a more fragmentary state. Beyond these, the fin continued outward into bony rays in the ordinary way, so that the digits were not free fingers projecting beyond the fin edge. They were embedded inside the fin, within the webbing, still functionally part of the lobed fin architecture. But they were present. They were articulated. They occupied, anatomically, the same topological position as the digits in the hand of a tetrapod. Nothing like this had been seen clearly in a fish before. What the Cloutier paper proposed, and what most of the field has since accepted with varying degrees of caution, is that the skeletal precursors of fingers existed, in recognizable form, inside the fins of fish before any vertebrate had limbs in the tetrapod sense. The hand, in other words, was not an invention of the first land animals. It was a rearrangement of elements that were already present in the water. Elpistostege may not have been the direct ancestor of tetrapods. The term is precise, and the evidence for direct ancestry is never complete. But its body shows that the Elpistostegalian lineage had, in at least one of its branches, already begun assembling a distal fin skeleton of the kind that later tetrapods would build their hands from. This changes the weight of the story in a specific way. If Elpistostege has digit-like bones in its fin, and Tiktaalik has a wrist, and Panderichthys, known from less complete material, but examined carefully by the paleontologists Catherine Boisvert, Elgar Mark Kurik, and Per Alberg in 2008, has its own version of distal fin bones consistent with the same pattern, then what we are seeing in the late Devonian is not a single fish quietly inventing the future of land vertebrates. We are seeing 3 related lineages on 3 different continents of the time, arriving at similar solutions to a similar problem in parallel. The problem, as we have already glimpsed, was shallow water. Specifically, the challenge of moving a large predatory body through root tangles and submerged debris and soft mud in oxygen-variable conditions, while retaining the ability to hunt effectively. The solutions, worked out independently in the Baltic, in the Canadian Arctic, and in what would become Quebec, were nearly identical. Flatten the skull, free the head from the shoulder, strengthen the fin base, add joints, carry a lung. This is the pattern evolutionary biologists call convergent evolution, and it is one of the most reliable signatures of selection's logic. When the same environment presents the same problem repeatedly to populations that are related but not identical, the solutions tend to resemble each other. Not because any of the animals are copying each other, or because some underlying design is expressing itself in parallel, or because there is a right answer the process is seeking. The resemblances emerge because the space of workable solutions, given the physics and the available biological toolkit, is narrower than the space of imaginable solutions. There are only so many ways to make a heavy-bodied predator work in a meter of warm, root-filled water. Different lineages found similar ones, independently, because similar constraints yielded similar outputs. A designer, faced with 3 separate commissions, might have produced 3 different aesthetic answers. Natural selection, faced with 3 separate populations under the same pressure, produced 3 versions of essentially the same animal. The word independently is carrying real weight in that paragraph, and it is worth examining. The Elpistostegalian lineages were not strangers to each other in the deep phylogenetic sense. They shared an ancestor somewhere in the earlier Devonian, and they inherited from that ancestor a great deal of common biology: the lung, the lobed fin, the humerus radius ulnar arrangement, the general body plan. What they did not inherit was the specific suite of later modifications that made each of them recognizable as an Elpistostegalian. Those appear to have been assembled in each lineage after the lineages had already diverged, not because each one set out on a journey toward flatness and mobility, because the shallow water kept rewarding the same kinds of bodies and the populations kept, on average, drifting in the same direction. There is something quietly clarifying about this when you hold it against the popular image of a heroic single fish. The image of a single fish stepping onto the shore carries an implied story about uniqueness. One creature, one moment, one crossing. The actual record, as it has filled in over the past 3 decades, carries a different shape. Several creatures across several million years, in several river systems on several continents, under the same slow pressure, accumulating the same kinds of features. Some of those lineages died out without leaving descendants that mattered. Some left descendants that later survived the end Devonian extinction. Some gave rise to what would eventually become the tetrapod radiation. Which lineage exactly sits on the direct line leading to you is a question the fossil record may never fully resolve. What the fossil record does resolve now is that the transition was not the work of a single fish. It was the work of a family of fish, all making the same kind of living in different places all at once. If you want a way to feel how this particular chapter has touched your own body, look at your hand again. Not the whole hand, just the thumb. Rotate it in a small circle in front of you. You can do this because the base of your thumb, the joint that connects it to your wrist, is a saddle joint, one of the most mobile joints in the human body. It is the reason your species has been able to make and hold tools, play stringed instruments, and perform most of the fine manual tasks that separate you practically from other primates. It is often described as one of the crown features of the human hand. It is also, in its fundamental construction, a refined version of a joint that was already present in early form in the distal fin skeletons of animals like Elpistostege. The elements that allow your thumb to oppose the other fingers were drafted, in crude outline, in the fin of a Devonian fish. Nothing new was added. The existing pieces were modified across a long succession of intermediate animals, and the modifications produced a joint that still mostly does what the original did: grip, twist, stabilize, but now does it against a door handle rather than a water-soaked log. The animals whose fins carried those first drafts had no idea any of this was going on. They were hunting in rivers that no longer exist, on coastlines that have long since become mountains or seabeds or sheets of ice. Their kind came and went. Only the bones and the arrangement of bones inside their bones remained, to be carried forward in lineages they never met, and to be rediscovered inside a CT scanner in Quebec, 380 million years later, by a team of humans whose hands were themselves the distant inheritance of what the scan was looking at. The rocks of East Greenland have produced some of the most important fossils in the entire history of paleontology, and for most of the 20th century they did so quietly, in the hands of a small number of people who kept returning to the same cliffs, in one of the least hospitable field environments on Earth, because the rocks there preserve a period of time that almost nowhere else does. These are the late Devonian sediments of what is called the Celsius-Bjerg group, laid down on the eastern margin of the ancient continent of Laurussia, about 365 million years ago. The landscape today is a fjord coastline of dark cliffs and cold seawater. accessible for only a handful of weeks each summer, and the fossils it has given up have, more than once, forced the whole field to reconsider how the transition from water to land actually happened. Two of those fossils carry the names Ichthyostega and Acanthostega, and they are, for practical purposes, the earliest well-known tetrapods. Both were described in preliminary form in the 1930s by the Swedish paleontologist Gunnar Säve Söderberg and later by his colleague Erik Jarvik, working from specimens collected during Danish expeditions to Greenland. Ichthyostega was published first and more thoroughly, and for several decades it stood alone as the representative animal of the water-to-land transition in every textbook that mentioned the subject. The popular image of a heavy-bodied salamander-shaped creature pulling itself up out of the mud on four splayed legs comes directly from early reconstructions of Ichthyostega. That image is so deeply embedded in public thinking about evolution that it has become a kind of visual shorthand for the whole story. It is also, as more recent work has shown, in several important respects wrong. The revision began in 1987, when a joint expedition from the universities of Copenhagen and Cambridge returned to the Greenland site, following up on a small collection of Acanthostega fragments that had been found some years earlier by a geology student working on something entirely unrelated. The Cambridge member of that expedition was Jennifer Clack, who would go on to become the most important researcher of early tetrapod evolution of her generation, and who passed away in 2020 after a career that essentially rebuilt the field from the ground up. What the expedition recovered over several difficult field seasons was a series of articulated Acanthostega specimens of a kind that had never been available before. Whole animals preserved well enough to show the anatomy at a level of detail the fragmentary 1930s material had only hinted at. The preparation took years. What emerged by the early 1990s changed the picture of the animal completely. Acanthostega had limbs. That had been suspected from the start. What was not suspected, what no one had seen in any earlier tetrapod, and what no one had predicted from the theoretical work on limb development, was how many digits the limbs carried. Clack, working with her colleague Michael Coates, found that the forelimb of Acanthostega ended in 8 fingers, not 5. 8. And a parallel re-examination of the hind limb of Ichthyostega, prompted by the Acanthostega result, showed that it carried 7. A third Devonian tetrapod, Tulapeton, known from Russia and described a few years earlier, turned out on reconsideration to have 6. The number 5, which for more than 300 million years has been the standard count for tetrapod digits, the basis of the word pentadactyl, and the number built into the hands and feet of nearly every living four-limbed animal, was not, as had long been assumed, the primitive condition. The earliest tetrapods were polydactylous. They had more fingers than we do. The 5-digit pattern came later as a refinement, not as the starting point. This was a serious revision. But it was not the deepest thing the Acanthostega material established. The deepest thing, and the one that most reshaped how paleontologists think about the transition, was what the rest of the body showed. Acanthostega had gills, functional internal gills, of the same kind a fish uses to breathe in water. Its tail was finned like a fish's, with bony rays supporting the tail fin proper. Its ribs were short and unlikely to have supported much weight on land. Its limbs, for all that they ended in fingers, were short-boned and weakly articulated, with the humerus and femur in particular showing features more consistent with levering a body through dense aquatic vegetation than with lifting a body against gravity. In almost every functional respect, breathing, propulsion, weight-bearing, posture, Acanthostega was an animal built for life in water. Its feet, with their 8 digits apiece, had not been built to walk on ground. They had been built to move through the dense, submerged, plant-choked shallows that its body occupied. Clack stated the implication directly, in a series of papers through the 1990s and eventually in her book Gaining Ground, published in 2002. Feet evolved underwater. They did not evolve for walking, they were selected, within an aquatic lineage, for exactly the kind of uses Acanthostega's body suggests, bracing against submerged debris, pushing through root tangles, stabilizing a heavy predatory body in variable shallow currents. The transition from fins to limbs, which had been told for most of a century as a story of fish gradually pulling themselves ashore, turned out to have happened largely in the water for water-based reasons. The land came into the story afterwards. What later tetrapods did over the following tens of millions of years was take a limb that had been designed, forgive the word for a moment, for aquatic use and repurpose it once again for something its original owners had never required. This is the kind of correction that does not usually reach the popular imagination, and it is worth taking seriously because it changes what the fossil sequence is actually showing. What the late Devonian record now gives us, read honestly, is not a ladder of animals gradually approaching the shore. It is a radiation of water-adapted bodies in a range of related lineages, experimenting with different solutions to the challenges of shallow, oxygen-variable, vegetated aquatic life, different numbers of digits, different limb proportions, different skull shapes, different balances of fin and limb. Some of these animals may have occasionally pulled themselves onto mudflats. Most probably did not. The animals we later came to call the first tetrapods were, in their own lives, almost entirely fish in every way that mattered to them, except for one suite of features, 4 limbs with digits, that had evolved inside the water for uses that had nothing to do with land. Something worth saying aloud in the middle of this, before the story continues. Acanthostega did not know it was the first of anything. Ichthyostega did not know it was the first of anything. Tulerpeton did not know it was anywhere at all on a timeline of vertebrate evolution, because Tulerpeton was a Devonian animal, and the concept of deep time had not yet been invented by anyone, and would not be invented for another 364 million years, by a species that did not yet exist. The words first and earliest, as we apply them, are not descriptions of the animals. They are descriptions of the fossil record we happen to have access to. An Acanthostega in the shallows of Greenland was not a pioneer. It was a Devonian tetrapod, a standard member of a then-existing group doing what its kind did for a living, hunting, breeding, breathing, eventually dying, with no sense of being at the beginning of a sequence, because there was no sequence to be at the beginning of yet. The sequence became a sequence later, in retrospect, when animals came into existence who could look back and count. This is a strange kind of fact to sit with, because the temptation to give the Devonian tetrapods some dignity of arrival, some sense of having crossed a threshold, is almost overwhelming in English. We speak of them as the first walkers, as the animals that brought life onto land, as the ancestors that made all subsequent vertebrate life possible. All of these phrases are comforting, and all of them are, in the strict sense, backwards. No animal brought life onto land. Life arrived on land piecemeal, across tens of millions of years, in the bodies of animals that were, each one of them, simply trying to live. The threshold is a thing we can see because the view from here is long. From inside the Devonian, the threshold is not visible. There is only water, and shallow water, and mud at the edges, and in some places and at some times, the slow drying of a pond that makes one kind of body a little more likely to leave descendants than another. The animals involved are not crossing anything. They are living and dying, and the statistical residue of all their living and dying, aggregated across millions of generations, is what later gets called a transition. If you want a place in your own body that belongs particularly to this chapter, count your fingers. There are 5 of them on each hand, and you have known that for so long that the number probably feels inevitable, as if it were simply the right number for a primate to have. It is not the right number. It is a settled number. The Devonian experiments with 7, 8, and 6 digits did not fail because those counts were wrong. They failed because the lineages that carried them, Acanthostega, Ichthyostega, Tulerpeton, did not, in the end, leave surviving descendants beyond the Devonian Carboniferous boundary in numbers that mattered. The lineages that did leave such descendants happened, for reasons that probably involve a combination of developmental constraint and historical accident, to be carrying 5. Once the 5-digit pattern was established in the early Carboniferous, it became very difficult to change. The genetic and developmental machinery that patterns a hand or a foot is deeply conservative, and any variation that tries to add or subtract a whole digit tends to cascade into other consequences that rarely survive selection. So the number stuck, not because 5 is optimal, because 5 is what the survivors happen to have. You are carrying, on each hand, a frozen outcome of a Devonian draw. Your thumb and the 4 fingers beside it are the arithmetic of a radiation that tried other numbers and in the branches that led to you did not keep them. A hand with 8 fingers, or 7 or 6, was a possibility once. It was, in the 95% saltwater shallow flats of what is now Greenland, an actual fact, on the forelimb of an animal about 60 centimeters long that lived and died without knowing it was anything worth naming. And your 5 are what remained, 365 million years downstream, because of deaths and survivals so numerous and so ordinary that no single generation of animals would ever have been in a position to notice them happening. That, finally, is what this part of the story is really about. Not the triumph of the first walkers, not the arrival of tetrapods on land. The quiet, indifferent, uncounted attrition of animals that were just animals, whose limbs did what their limbs could do, whose lives ran their length, and whose deaths, all of them, uniformly and without exception, contributed as much as any survival did to the shape of the hand you are looking at right now. In 2010, the journal Nature published a paper that should not, according to the story most of us had been telling, have been possible. The paper was titled, straightforwardly, Tetrapod Trackways from the Early Middle Devonian Period of Poland, and its lead author was a Polish paleontologist named Grzegorz Niedźwiecki, working with Per Alberg at Uppsala and colleagues at the University of Warsaw. The claim was narrow, technical, and extraordinary. In a disused limestone quarry in the Holy Cross Mountains of central Poland, at a place called Zachełmie, the team had found a series of preserved footprints. The prints were not fragments or impressions one could argue about in isolation. They were articulated trackways, sequences of footfalls, manus and pes left by a quadrupedal animal walking across what had once been soft sediment. Some of the trackways were long enough to show the alternating rhythm of a real gait. Some of the individual prints were clear enough to show toes. The rocks they were preserved in belonged to the Wojciechowice Formation, a carbonate unit that had been dated by conodont biostratigraphy and by its stratigraphic position to the Eifelian stage of the Middle Devonian, approximately 395 million years old. That is the difficulty. Tiktaalik, the most convincing intermediate body fossil in the Elpistostegalian lineage, lived about 375 million years ago. Acanthostega and Ichthyostega, the earliest known tetrapod body fossils, are about 365 million years old. The Zachełmie tracks, if the dating holds, and if the interpretation of the prints is correct, are 18 million years older than the oldest tetrapod body fossils and roughly 10 million years older than the oldest Elpistostegalians. Something was walking in Poland, four-limbed and digit-bearing, long before the animals that are supposed to represent the intermediate stage of the transition. This is the kind of result that, if true, rearranges the whole story. The transition from fish with arm skeletons in fins to tetrapods with digits does not, on this evidence, fit into the 15-million-year window that the fossil sequence from Panderichthys through Tiktaalik to Acanthostega had neatly implied. It either happened much earlier, leaving body fossils that we have not yet found, or the creatures that made the Zacheumi tracks were already tetrapod-grade animals, while their supposed ancestors were still swimming around as Elpistostegalian fish in what is now Quebec and the Canadian Arctic. Neither possibility is comfortable. The first requires accepting a large silence in the body fossil record, 15 to 20 million years of tetrapod evolution with almost no bones to show for it. The second requires that the animals we have been calling intermediate were not actually intermediate at their own time, but late surviving representatives of an earlier grade, contemporaneous with more advanced relatives that left no body fossils but did leave footprints. The paper's authors argued for the first possibility. Their position was that the tracks are genuine tetrapod trackways, the dating is secure, and the implication is that the body fossil record is seriously incomplete. The missing animals, the ones that actually made these prints, existed, but either did not fossilize well or have not yet been found. What Zacheumi shows on this reading is that we have been looking at the fish-tetrapod transition through a keyhole, and that the actual dimensions of the room on the other side are larger than we had supposed. It is worth being clear about how the discoverers of Tiktaalik responded to this, because their reaction says something important about how science works when it runs into a result it was not expecting. Ted Deichler, in interviews at the time, was unwilling to modify his view of the transition based on trace evidence alone. Footprints, in his argument, are not bones. The identity of the track maker cannot be established with the same confidence as the identity of an animal whose skeleton you have in hand. Neil Shubin took a more layered position. His initial response was to note that an animal like Tiktaalik, walking across a soft substrate, could have produced very similar-looking tracks, that is, that the Zacheumi prints might not require a fully evolved tetrapod to explain. Over the following years, his view modified further. Some of the Zacheumi tracks, he suggested, particularly those that lacked clear digit impressions, might have been made by something more fish-like than the original paper had implied. The counter-arguments have continued. A paleontologist named Spencer Lucas, reviewing the tracks in 2015 and again more recently, has argued that many of the features the original team interpreted as footprints may in fact be feeding traces, marks left in soft sediment by fish moving along the bottom, or possibly fish nests. Per Ahlberg, one of the original authors, has pushed back on that reading in turn. A separate study led by Martin Kvarnström reinterpreted the depositional environment of the track-bearing rocks, arguing that the setting was a series of ephemeral lakes rather than the tidal flats originally proposed, which would actually strengthen the case for terrestrial locomotion by the track makers. The debate is ongoing. There is no consensus. There is, at the moment, a reasonable body of paleontologists who think the Zacheumi tracks are the oldest direct evidence of tetrapods anywhere in the fossil record, and there is a smaller but serious body of paleontologists who think they are something else. What this should do for anyone following the story is make clear something about the shape of the science that the previous chapters have mostly managed to smooth over. The narrative of the transition from fish to tetrapods, as it is usually told, proceeds as if the evidence arrives in a clean sequence and yields a clean interpretation. Eusthenopteron first, Tiktaalik next, Acanthostega after that. The shape of the lineage implied by these animals, laid out in their right stratigraphic order, is as tidy as a genealogy. The truth is that the evidence is always less clean than the narrative makes it sound. Fossils are scarce. Dating carries real uncertainty. The identity of a track maker is almost always debatable. The pattern of preservation in the rock record is deeply uneven, biased towards certain environments and certain body types, and completely blank for large stretches of geography and time that must have been full of animals we will never see. Every clean story about deep time biology is, at some level, a story told around its gaps. Zacheomi is, among other things, a reminder that the gaps are not always where we think they are. What we can say about this chapter of the story, honestly, is narrower than we would like. Something made tracks in what is now Poland 395 million years ago. Those tracks, on the available evidence, show features consistent with a four-limbed, digit-bearing animal walking across soft sediment. Whether the tracks were made by a full-grade tetrapod, a Tiktaalik-like Elpistostege stretching its interpretive range, or some kind of fish behavior we have not yet imagined, is genuinely unresolved. Whether the transition from fish to tetrapod happened in the neat 15 million year window the body fossils suggest, or in a much longer and more complicated window that includes animals we have not yet found, is also genuinely unresolved. The best paleontologists in the field disagree about both questions, and they disagree with the care and restraint of people who know they might be wrong. There is a temptation, when a story is going well, to treat scientific uncertainty as a kind of loose end that needs to be tucked away. It is worth resisting that temptation because the uncertainty is not a loose end. It is the texture of how the knowledge is actually made. When a paper like Niedzwiecki's arrives in the middle of a well-established narrative and genuinely unsettles it, the result is not failure. The result is that the narrative gets better, less neat probably, but more honest about the state of the evidence. The first versions of this story, written in the 1930s, had no Acanthostega to work with and no Tiktaalik. The versions from the 1990s had Acanthostega, but no polydactyly firmly established, and certainly no Zacheomi. The version you are listening to now is, at best, a version of the story that has absorbed the Zacheomi tracks into its footnotes and will look different again in 10 or 20 years, when another quarry in some part of the world we are not currently watching gives up another piece of the record we are not yet expecting. If you want to put this chapter somewhere in your own body, think for a moment about the way you walk, not the mechanics of it, the specific timing of it. When you take a step, the right foot and the left hand move roughly in parallel, then the left foot and the right hand. This diagonal coupling, in which limbs on opposite sides of the body swing together, is the default gait pattern of almost every four-limbed vertebrate that has ever been reconstructed from footprint evidence. It is called a lateral sequence gait, and it is visible in the Zacheomi trackways themselves in the spacing of manus prints relative to pes prints. Whatever made those marks in the Polish sediment 395 million years ago was already moving its legs the way your legs moved the last time you crossed a room. The choreography of a walk, which limb fires when, how the body balances across the transfer, where the weight passes from contact to contact, is that old. It existed in animals whose names we do not yet know, in places whose maps we cannot fully reconstruct, in bodies whose anatomy we have not yet recovered from stone. But the pattern is there, in the prints, and the pattern is identical to yours. This is what Zacheomi is actually offering, underneath the dating controversy and the contested interpretations. It is offering the possibility that the way you walk is older than the oldest body fossils that should, according to the tidy version, have been able to walk that way at all. The evidence is indirect, the debate is real, but the tracks are there, preserved in dolomitic limestone in a disused Polish quarry, and whatever made them was walking, roughly as you walk, in a world where the animals that are supposed to have first walked had not yet officially appeared. Around the 6th week of your own development, when you were a curled thing smaller than a grain of rice, something began to happen at each of the 4 points on your body where limbs were going to be. The cells in those regions, which had until then been ordinary enough members of the embryonic wall, started to behave differently. They proliferated faster. They formed a small outward bulge called a limb bud, shaped roughly like a paddle. Over the following days, the paddle grew, and a specific set of genes within those cells began to switch on in a specific order, and those genes, proteins really, made from those genes, instructed different parts of the bud to become different parts of the limb. One region of the bud was told to become the upper arm with its single bone. A region further out was told to become the forearm with its 2 bones. A region further out still was told to become the wrist, and then at the very tip, a region was told to become the hand, and within that region 5 separate zones were told to become 5 separate digits. None of this instruction was particular to you. The same genes do the same work in every 4-limbed vertebrate that has been examined for it. They are called the Hox genes, and they are among the most deeply conserved regulatory genes in animal biology. A Hox gene taken from a mouse, spliced into a fly embryo, will produce the corresponding body part instruction in the fly, because the fundamental chemical grammar the genes are written in has been essentially stable for more than 500 million years. In the specific case of limb development, 2 clusters of Hox genes, labeled Hox-A and Hox-D, are responsible for most of the heavy work. Within each cluster, the genes are arranged along the chromosome in an order that mirrors the order in which they will be deployed along the developing limb. The genes that pattern the upper arm sit at one end of the cluster, the genes that pattern the hand sit at the other, and the cells read the cluster roughly in sequence, from base to tip, as the limb grows outward. The fact that this system exists in you is not in itself surprising. You are a 4-limbed vertebrate, and 4-limbed vertebrates all build their limbs this way. What is surprising, and what forms the substance of this chapter, is that the same system, the same genes in the same clusters, doing recognizably the same work, is also present in fish that have never had limbs, in fish whose fins look nothing like arms. In zebrafish, the ordinary striped aquarium species whose embryos have been one of the most heavily studied organisms in developmental biology for the past several decades. The Hox-A and Hox-D clusters in a zebrafish embryo turn on in the same temporal sequence they turn on in a mouse, in cells that will build a pectoral fin rather than an arm. And the cells that are doing the building read those genes and interpret them and use the information to make the structure the fish needs. The genes do not know whether the cells they are instructing will end up as a fin or as a hand. They issue the same instructions either way. This was not always an obvious fact. For most of the 20th century, the consensus view held that tetrapod digits were a true evolutionary novelty. New structures, genuinely invented in the lineage that led to the first tetrapods without a clear precursor in the fins of any fish. The limb development work done on mice and chickens through the 1990s mapped out the Hox gene network in impressive detail, and as the work matured, it became possible to ask a more specific question. Where, in the fish fin, was the genetic signal that corresponded to the tetrapod hand? The obvious answer would have been nowhere, that the hand was new and that its patterning system was also new. But a series of careful comparative studies, mostly conducted in the past 2 decades, has come to a different answer. The most decisive of those studies was published by a team at the University of Chicago in 2016. The senior author was Neil Shubin, the same paleontologist who had been digging at Ellesmere Island a decade earlier, and the first author was a developmental biologist named Tetsuya Nakamura. What the team did, in broad terms, was use the CRISPR gene editing system. which was at that point just becoming available as a reliable laboratory tool to knock out the Hox genes responsible for late-phase digit patterning in zebrafish embryos and then observe what happened to the fin as it grew. If the genes in question were, as the older consensus suggested, irrelevant to fin construction, if they were real instructions for building a hand but not involved in building a fin, then deleting them should have made no significant difference to the zebrafish fin. If, on the other hand, the genes were doing something in the fin that we had not previously recognized, then deleting them should disrupt the fin in some specific, revealing way. The deletion disrupted the fin in a very specific, very revealing way. In the zebrafish embryos, with the relevant Hox genes knocked out, the fin rays, the lepidotrichia, the long fringed dermal bones that make up most of a fish's fin surface, did not form properly. They were reduced. Meanwhile, at the same location in the fin, the small internal bones called endochondral radials, the bones that, in a tetrapod limb, correspond to the bones of the wrist and the digits, were increased in number. The genes the team had deleted were, in other words, actively involved in the normal construction of a fin, but were being used to build the outer, ray-based part of the fin rather than the inner, bony part. When those genes were removed, the cells that would have become fin ray makers became endochondral bone makers instead. The fin, in the knockout embryos, started to look less like a fin and more like a rudimentary limb with a larger cluster of internal bones and a shortened fringe of rays. The interpretation the authors proposed, and which has since been broadly accepted, is that the fin rays and the digits share a common developmental history at the cellular level. They are not alternative structures patterned by different systems. They are alternative outputs of the same system, the same Hox gene instructions, interpreted differently by cells in different evolutionary contexts. In a fish, the cells responding to the late-phase Hox signals migrate outward to the edge of the fin and become fin ray-producing cells. In a tetrapod, the same cells, responding to essentially the same signals, stay closer in and become finger-producing cells. The difference between a fin and a hand, at the level of the underlying genetics, is not a difference in the instructions. It is a difference in how cells interpret the instructions. What this means for the story we have been following is worth sitting with. The evolution of the tetrapod hand, as told through the fossil record, Eusthenopteron first, then Tiktaalik, then Elpistostege, then Acanthostega, then the settled pentadactyl pattern of the Carboniferous, looks, in fossil form, like a gradual accumulation of new structures. Humerus first, radius and ulna next, wrist bones next, digits at the end. Each innovation appears in the rock record as a new feature added to the lineage. But in molecular reality, almost none of these features were genuinely new in the deep sense. The humerus was a bone that had been there for far longer. The digit patterning genes were active in fish that never had digits. The regulatory elements that control them, the small stretches of non-coding DNA that decide when and where the Hox genes turn on, were already present in the genomes of sharks, paddlefish and zebrafish doing related work. In some cases, fish regulatory sequences can be spliced into mouse genomes and will drive limb development in the mouse exactly as the mouse's own regulatory sequences would. The genetic machinery that was going to build a hand was already sitting in the cells of fish that had never had one, waiting for a context in which a different cellular interpretation of the same instructions would produce a different structure. This is not a metaphor or a rhetorical flourish, it is a literal fact about the conservation of regulatory genetics across the vertebrate lineage. The hand was not invented, it was, in a precise and experimentally demonstrated sense, drafted. The instructions had been written long before the structure existed. What changed, across the long transition we have been tracing, was not the fundamental code, but the context in which the code was being read, the shape of the cells, the timing of their movements, the relative rates at which the fin-ray-making cells and the endochondral bone-making cells responded to the shared signals. Adjustments in context, rather than innovations in content, did most of the work of turning a fin into a limb. There is a quiet philosophical implication in this which is worth naming. One of the oldest intuitions people have about evolution is that really significant change must require really significant new material, new genes, new structures, new building blocks assembled from whole cloth. The deep comparative genetics of the past 20 years has slowly dismantled that intuition. What it has replaced it with is a stranger and, on reflection, more elegant picture, in which the major transitions of animal evolution happen mostly by reinterpretation of existing machinery rather than by acquisition of new machinery. The tool was already there. The hand was a question of how and when and where the tool was used. And this same pattern appears again and again across the history of animal bodies. The eye, the feather, the placenta, the brain, each one built, at its core, from older components repurposed into a new configuration rather than synthesized from scratch. If you want a place in your body where this chapter particularly lives, hold your hand up in front of you and spread your fingers. Look at the webbing between them, the short stretches of skin that bridge the base of each finger to the next. That webbing, which barely registers as a feature of the adult hand, is the remnant of something larger. When you were in the 6th week of development, your hand was not a hand. It was a paddle, a flat plate of cells with 5 internal rays converging toward its end. The spaces between the rays were filled in, at that stage, with living tissue, so that the paddle had no fingers at all, just a continuous surface. The fingers appeared over the following 2 weeks, not by growing out, but by dying back. The cells in the regions between the prospective digits received a genetic signal instructing them to die, and they died one by one in a process called programmed cell death. The fingers are what remained after the in-between tissue disappeared. The webbing at the base of your fingers is the only part of that tissue that escaped the signal. The paddle you started with was, at that stage, not very different in its fundamental plan from the distal end of the fin of a Devonian Elpistostegalian embryo. If such an embryo had ever been preserved for us to examine, which none ever has been, the dying back process that carved your fingers out of that paddle is an evolutionary refinement of a much older cellular mechanism that, in fish, regulates the way fin-ray-making cells migrate to the edge of the fin. The hand you have is, underneath everything, a fin that was made fewer and sculpted differently. The instructions were already there. What changed across 375 million years was how the cells that read the instructions decided in the end to interpret them. Take a slow breath now, if you can do so without interrupting your attention. Feel the air move down through the back of your throat. Notice where it goes. Somewhere behind your collarbones, the path you just swallowed air down is only a few centimeters away from another path. The one food goes down when you eat, and the two of them cross. They share a common entrance at the back of the mouth, and they separate only at the top of the throat, where a small cartilage flap called the epiglottis tips forward over the breathing tube every time you swallow, diverting the food around it and down into the esophagus. When the diversion fails, even slightly, you inhale your food. When it fails more severely, you choke. Every person who has ever lived has inherited a respiratory system whose intake shares a vestibule with the digestive system, which is why choking is a leading cause of accidental death in human beings, particularly in the very young and the very old. No engineer would have built it this way. Nothing about it is efficient. It is instead the way it is because of the order in which its parts became important, in animals whose living arrangements were, for a very long time, nothing like yours. To understand why the plumbing crosses in your chest the way it does, we have to go back to a fact that has been waiting in the background of this whole story, and that is worth stating plainly now. Lungs did not evolve for life on land. Lungs evolved in fish. They were there in recognizable form tens of millions of years before any vertebrate had stepped out of water, and when the first tetrapods took the structures onto shore, they were not inventing a way to breathe air, they were inheriting one. The evidence for this is clear, and it comes from several directions. Living lungfish, a small group of freshwater sarcopterygians, represented today by 6 species distributed across Africa, South America and Australia, have paired vascularized sacs connected to the digestive tract, which they use to breathe air directly at the surface of the water. African lungfish in particular can survive for months out of water, buried in hardened mud during the dry season, with their lungs doing essentially all of their respiratory work. These lungs are not a recent invention. They are homologous, structurally, developmentally, and genetically, to your own lungs. The condition they represent, air-breathing supplementation of gill respiration, appears to have been present in the common ancestor of all bony fish, including the sarcopterygians on one branch and the ray-finned fish on the other. In the ray-finned branch, which contains most of the fish species alive today, the ancestral lung was gradually modified in most lineages into a gas-filled organ used for buoyancy control rather than breathing. That organ is called the swim bladder. The swim bladder and the lung are the same thing. The swim bladder is what the lung became in fish that no longer needed to breathe air. The lung is what the swim bladder stayed in fish that did. The order here matters. The lung came first, the swim bladder came from it. In the version of the story where lungs evolve for land life, the relationship would run the other way. Swim bladders would be the primitive condition, and lungs would be modifications of them, appearing late in the fish lineage as some groups started to gasp at the surface of drying pools. That version is not what the evidence shows. The evidence shows that air-breathing supplementation was a general feature of early bony fish, present in the ancestor of the entire group, and that it was used for the purposes you would expect it to be used for, surviving stagnant, warm, oxygen-poor, shallow water. The kind of water, in other words, that we have been visiting in previous chapters. Devonian rivers, swampy margins, seasonally drying ponds, the shallow carbonate flats that left the Zakelme tracks. In all of those environments, a fish that could gulp air at the surface had a measurable advantage over a fish that could not. That advantage is why lungs existed in the water, well before they would matter on land. This is the crucial reframing. When the ancestors of the first tetrapods began to spend more time near the surface, near the air-water interface, and eventually in temporary excursions onto mudflats and shorelines, the breathing apparatus they were using in those moments was not new. It was the same organ their aquatic relatives had been using in the same kind of water. Every trip out of water for every early tetrapod was carried by a lung that had evolved for a slightly different purpose, supplementing gill respiration in oxygen-poor water. And that happened to work, with some modification in air. The transition to terrestrial breathing was not a transition to a new organ, it was a transition in how an existing organ was weighted. More air, fewer gills, more reliance on the lung, less on the gill arches. Gradually, over the tens of millions of years that followed, the gills were lost, the lungs took over entirely, and the ribs and chest muscles were reorganized to pump air in and out of the lungs more efficiently. But the organ itself had been present and functional for a very long time before any of this became necessary, which brings us back to the crossing in your chest. A fish with lungs has to get air from outside the body to the lung sac. The most economical way for a fish to do that, given the structure it already has, is to pull air in through the mouth, just as it would pull water in, and to connect the mouth to the lung by a short tube leading down from the roof of the mouth or the side of the throat. That is, in fact, exactly how lungfish do it. The tube that connects the mouth to the lung in a lungfish is a modified portion of the same tube that connects the mouth to the gut. The digestive tract, in other words, is also, at its upper end, the respiratory tract, and the lung is attached to it as a side branch. Food and air travel through the same passage at the top and then diverge. This arrangement works for a fish. The fish is never doing two things with its mouth at once. It either eats or it breathes, and the two activities are separated in time rather than in space. There is no structural problem with routing them both through the same opening and the same tube. The system is minimal, elegant, and perfectly adapted to the life of a fish. What happens over evolutionary time is that this system gets inherited by tetrapods. The Sarcopterygian ancestor of the first tetrapods already had the basic plumbing: mouth, shared passage, lung as a ventral outgrowth of the foregut. When the transition to life on land slowly shifted the respiratory balance from gills to lungs, and when breathing started to happen continuously rather than intermittently, the plumbing stayed the way it was. Nothing rebuilt it. Selection did not go back to the drawing board and separate the tube that carries air from the tube that carries food, because there was no drawing board and there was no separation available in the existing material to select for. The tubes continued to share an opening, and they continued to share a passage at their upper end, and all that changed was that the flap valve system at the divergence point became more elaborate to handle the fact that breathing was now constant rather than occasional. The result is the crossing. Food and air enter your body through the same opening. They travel through a shared passage, the pharynx, for several centimeters. At the bottom of that passage, they split. The esophagus continues downward behind the trachea, and the trachea ducks away in front, and a small hinged flap, the epiglottis, closes over the trachea every time you swallow, so that food is directed around it and into the esophagus rather than down into the airway. Most of the time, the system works. Millions of times a day, across billions of people, food goes the right way. But the system is fundamentally vulnerable. Any lapse in the coordination between swallowing and breathing, from a moment's distraction, from the weakness of age, from the looseness of very early infancy, from a laugh that catches at the wrong moment, can root food into the lung, and then the body has to cough the food back out, or if it cannot, the person dies. The leading cause of accidental death in Americans over 65 is not a car crash, and it is not a fall, and it is not even a stroke or heart attack. For many subcategories of that population, the leading cause is choking. A designer would not have built this. A designer, given the task of supplying a land animal with continuous air intake, would almost certainly have routed the trachea through a separate opening, a blowhole, say, or a nostril-to-lung pathway that never touched the digestive tract at all. Whales and dolphins, which return to the water from a fully terrestrial ancestry, have in fact evolved something approaching this, with the nostril migrating to the top of the head and connecting directly to the lungs, bypassing the mouth entirely. The mammalian land lineage did not get there. It got stuck with the fish-inherited arrangement, and every refinement it made, the elaboration of the epiglottis, the coordination of swallowing reflexes, the careful timing of the respiratory cycle around eating, was a workaround for a problem that the original design did not anticipate, because the original design was not a design. It was a fish's plumbing doing fish things in water where breathing and eating were not simultaneous. This is the Dawkins reversal in its raw form, and the shape it takes here is worth sitting with. The respiratory system you are using right now to take in the air that is letting you listen to this voice is elegant enough that it almost never fails. It is the product of hundreds of millions of years of refinement, selection, and adjustment, and in its normal operation, it is genuinely impressive. It is also, in its fundamental layout, a suboptimal holdover. The elegance is at the level of the workaround. The layout underneath the workaround is what it has to be because of what the fish had. And fish in the water had no reason to build it any differently. If you want to feel the age of this arrangement, put one hand lightly on your throat, just below the chin, and swallow. You can feel the small structures shift upward and then return. That upward and back motion, which happens every time you swallow so many times a day that you have long stopped noticing it, is the physical evidence of a 365-million-year-old compromise. Your larynx rises to meet the epiglottis. The epiglottis tips forward over the airway. The food passes around it and down into the esophagus. The larynx returns to its resting position and the airway reopens. The whole movement takes less than a second. It is ancient. It is performed by every person in every conversation every time they swallow. It is the animal solution to a plumbing problem that should not have been there in the first place, and that is there because the animal started out in water where the problem did not exist. Breathing is the oldest act in your body, in the sense that it was the first thing a vertebrate ancestor did that you still do in recognizably the same way. But breathing air, specifically, is not the thing your lineage invented. Breathing air is the thing your lineage inherited, along with a set of geometrical consequences that it has never fully resolved, and that your throat carries at every swallow as a quiet record of where the breath originally came from. Somewhere inside each of your ears, behind the eardrum and shielded by the densest bone in your body, there is a chain of 3 small bones so delicate that all 3 of them together, laid flat in your palm, would weigh about as much as a grain of rice. They are the smallest bones anywhere in the human body, and they are essential. Without them, you could not hear a voice speaking at conversational volume. Without them, the air pressure changes that carry sound from the outside world would never reach the fluid-filled chamber of the inner ear, where they are finally converted into nerve signals. The 3 bones are called the malleus, the incus, and the stapes, the Latin words for hammer, anvil, and stirrup, and they work together as a tiny mechanical chain, transferring the vibrations of the eardrum inward with remarkable fidelity, across a distance of only a few millimeters, into the inner ear. This is the central mechanical fact of how a mammal listens. What is strange about these bones, and what has made them one of the most compelling stories in all of comparative anatomy, is that 2 of them did not start out as ear bones. The malleus and the incus, the hammer and the anvil, were originally parts of a reptile's jaw. They were structural elements of the joint, where the lower jaw met the skull, load-bearing bones that transmitted the force of a bite. The same bones, in the same position, can be found in the fossil skulls of mammal-like reptiles stretching back more than 250 million years, where they are called the articular and the quadrate, and where they are unmistakably working as a jaw joint. At some point during the long evolutionary passage from mammal-like reptiles to true mammals, these 2 bones migrated. Not all at once, and not by any single step, but gradually. Across tens of millions of years and dozens of intermediate species, they slid backward along the edge of the skull, became progressively smaller, lost their load-bearing role in biting, and were incorporated into the middle ear, where they took up a new job of transmitting vibration. The joint they used to form was replaced in the mammalian lineage by a different bone-to-bone articulation built from different skeletal elements. The old joint bones did not disappear. They were reassigned. The stapes, the third of the 3, has a separate history. It came not from the jaw, but from the upper gill arch of a fish, specifically from a structure called the hyomandibula, which in fish serves as a mechanical support connecting the brain case to the jaw. In the lineage that led to tetrapods, as the head separated from the shoulder girdle and the jaw mechanics reorganized, the hyomandibula lost its structural role and was repurposed first into a bone that transmitted ground-borne vibrations in early tetrapods, the columella, and later, in mammals, into the stapes, the third link in the middle ear chain. The passage from gill arch support to middle ear bone took even longer than the passage of the jaw bones. It began in the water, in animals that did not yet have anything we would recognize as ears at all. What this means, if you trace the three bones back through their histories, is that the apparatus mammals use to hear is built, essentially in its entirety, from pieces that were originally doing something else. The malleus and incus were once structural elements of a jaw joint. The stapes was once a strut bracing a fish's skull against its jaw. None of these bones evolved, in the usual sense of the word, for hearing. They were already in existence for other reasons, and they were slowly moved into new positions by the accumulating pressure of selection in a lineage of animals whose environmental niche happened to reward very sensitive airborne sound detection. The reason this story is known in such detail, and the reason it is sometimes offered as the single most beautiful example of exaptation in the entire evolutionary record, is that the transition has been documented by an unusually rich fossil sequence. Through the late Paleozoic and into the Mesozoic, a series of mammal-like reptiles, the synapsids, show in their preserved skulls every intermediate stage of the transition. In early synapsids, the articular and quadrate are full-sized jaw bones forming a functional jaw joint. In later synapsids, those bones begin to shrink, and a second jaw joint appears alongside them, formed by different elements, the dentary on the lower jaw and the squamosal on the upper. For a long period of geological time, the animals in this lineage had two jaw joints simultaneously, one made of the old bones and one made of the new bones, both functional, both contributing to the bite. In still later forms, the old joint bones continue to shrink while the new joint grows in importance. And in the earliest true mammals, the old bones have become so small and so reduced in their load-bearing role that they are functionally no longer part of the jaw. They have migrated backward, tucked in behind the new jaw joint, and begun their new life as part of the middle ear. The transition is visible, stage by stage, in the skulls of Thrinaxodon, Probinognathus, Morganucodon, and a number of other synapsid and early mammal genera, whose names are familiar mostly to paleontologists, but whose fossils have, together, provided a level of evolutionary documentation that is almost unique in its completeness. You can lay the skulls out in order and watch the bones change their shape, their size, and their position, one small step at a time, across millions of years. What you see is not a leap. It is a slow drift, in which the bones are doing one job at the beginning, two jobs for a long stretch of the middle, and a different job by the end. At no point is the transition discontinuous. At no point does the animal lack a functional jaw or a functional connection between its ear and the rest of its head. The new uses emerge alongside the old ones, take on more and more of the work, and eventually replace them, while the old structures simplify into something suited to their new role. Something about the geometry of this transition deserves a moment of attention. The jaw joint of a reptile is a load-bearing hinge. It has to be strong because it transmits the force of the bite. The middle ear bones of a mammal, by contrast, need to be as light and as mobile as possible because their function is to transmit tiny, rapid vibrations. These are almost opposite engineering requirements. The same bones, in the same basic positions, are asked to move from one extreme to the other. What made the shift possible was a long geological interval during which the bones were neither fully one thing nor fully the other. They were shrinking. They were losing their jaw roll slowly as the new jaw joint took over the bite. They were being held in position by ligaments that did not yet need to transmit vibration, but also did not need to transmit bite force. During that long intermediate phase, the bones had time to change, to become smaller, lighter, more suspended, without ever being asked to do a job they could not yet do. The transition worked because there was slack in the middle. The old roll was fading while the new roll was emerging, and neither was ever imposing its full demands on the bones at the same time. This is how almost all major exaptations seem to happen once you look at them closely. Not by bones or organs switching abruptly from one job to another, but by long stretches during which a structure is doing less than it used to do, or something on the side of what it used to do, or something both its old lineage and its new lineage could tolerate. The slack is where the change lives. Without the slack, the pressure to perform the old role would hold the structure in place and forbid any change. Without the slack, the new role would arrive too suddenly and find no structure ready to fill it. It is the reduction in the old function, the partial retreat, the fading, that opens the door for the new one. Exaptation is not a story of redeployment. It is a story of release. The implications for your own head are more concrete than they first sound. When you hear a voice right now, mine, or any voice near you, or the sound of your own breath, the pressure waves in the air are striking your eardrum. The eardrum vibrates. The vibration is passed across the middle ear by a chain that starts at the malleus, continues through the incus, and ends at the stapes. The stapes sits against a small oval window in the bone that encloses your inner ear, and its motion pushes the fluid inside, setting up waves that are read by hair cells lining a spiral called the cochlea. The hair cells translate the waves into electrical signals. The signals travel up the auditory nerve and into your brain. At the heart of that chain, two of the three mechanical components were, hundreds of millions of years ago, bones that your ancestors used to chew with. Every conversation you have ever had has been delivered to your consciousness by the dismantled remains of a reptilian jaw. If you want a small physical gesture that puts this into your present body, do the following. Clench your jaw lightly, not hard, just enough to feel the masseter muscle tense along the side of your cheek. Then release. Notice that you can hear your own heartbeat briefly, faintly, when you clench. That is because the act of clenching very slightly compresses the vessels supplying blood to the muscles around your jaw and face, and the pulsations of those vessels transmit into the bone, and the bone transmits into the middle ear, because the bones of your middle ear are still in mechanical contact with the rest of your skull. Your eardrum does not need to be involved. The sound can travel through bone. This is the same conduction path your lineage's ancestors were using hundreds of millions of years ago, when the ear bones were still part of the jaw, and when hearing meant detecting the vibration of the ground transmitted up through the skeleton to whatever organ could register it. The pathway is still there. The clench just reminds you that it is. There is one more thing worth mentioning about this transition, which is a particular irony of the fossil record. The intermediate synapsids, with their two jaw joints, the old one and the new one side by side, were, for a long time, considered oddities. Paleontologists in the 19th and early 20th centuries sometimes interpreted them as evolutionary experiments that had gone wrong, unstable forms that would have been outcompeted by cleaner designs. The double jaw joint looked, in the textbook of the day, like a design problem. It is not a design problem. It is a design solution, in the strict sense that it is the mechanism by which the transition could take place at all. Without a period in which both joints were present simultaneously, The old bones could never have shrunk enough to become ear bones, because the jaw would have failed the moment the old joint ceased to function. The double joint was not a mistake. It was the bridge on which the entire mammalian sense of hearing walked from one set of bones to another. The animals that carried it were not failed reptiles. They were successful enough, and long-lived enough as a group, to hand the transition forward. You are one of the things that made it forward. The chewing you do at dinner and the hearing you do at the same dinner are being performed by different descendants of bones that were once a single system. Your food is broken down by a joint that in your remote ancestors did not yet exist. The words spoken to you across the table are delivered by a joint that no longer does anything but carry sound. Both of those systems started out in the same place, on the side of a reptilian skull, and they separated over a very long interval of small, cumulative, non-dramatic changes into the two distinct machines you are using now, almost at the same moment, whenever you eat and listen. At the end of the Devonian period, something went wrong. The exact nature of what went wrong is still, more than a century after the problem was first formally recognized, a subject of active disagreement among paleontologists. But the shape of the outcome is clear. Between roughly 372 million years ago and the end of the period at 359 million years ago, the marine ecosystems of the planet underwent a long, uneven series of extinction events, concentrated at two boundaries now called the Kellwasser event and the Hagenberg event. The placoderms, the armored fish that had dominated Devonian seas, including Dunkleosteus, disappeared entirely. Many groups of corals were devastated, the great Devonian reef systems collapsed. Across roughly 20 million years of protracted biological stress, something in the order of 3/4 of all animal species on Earth were lost. The cumulative toll places the late Devonian as one of the 5 mass extinctions of the last half-billion years, comparable in magnitude to the end Cretaceous event that ended the non-avian dinosaurs. The causes are still debated. The most widely supported reconstructions involve some combination of global cooling, widespread anoxia in the oceans, a drop in dissolved oxygen so severe that large regions of the water column became uninhabitable, and changes in atmospheric chemistry driven, at least in part, by the very thing we have been watching build across previous chapters. The first true forests spreading across the continents had been drawing carbon out of the atmosphere at an unprecedented rate. Their root systems had been weathering the rocks they grew on, releasing nutrients that washed into the seas. The nutrient pulse fed enormous algal blooms, which consumed oxygen as they decomposed, which drove the anoxia, which killed the shallow marine ecosystems. The plants, in other words, appear to have contributed substantially to the collapse of the animal communities around them. This is not a claim about intent, it is a claim about geochemistry. The transformation of the continents into forested landscapes was an ecological revolution, and like most revolutions, it produced effects its participants could not have anticipated, including a mass extinction in the water. The early tetrapods, which by the end of the Devonian had been radiating modestly for several million years in the shallow margins of these ecosystems, were caught in this collapse. Acanthostega, Ichthyostega, Tulerpaton, and their close relatives all date to the last stages of the Devonian. After the Hagenberg event, the fossil record of tetrapods goes almost entirely silent. For a stretch of roughly 15 million years at the beginning of the Carboniferous period, from approximately 359 to 345 million years ago, there are almost no tetrapod fossils at all. Not because no tetrapods existed. Tetrapods must have existed during that interval because by its end, a fully diversified radiation of them reappears in the record, with features showing that considerable evolutionary change has occurred in the meantime. But for those 15 million years, the bodies of those animals are, for the most part, simply not preserved in rocks we can find. The gap is called Romer's Gap, after the American paleontologist Alfred Romer, who first drew attention to it in the middle of the 20th century. Romer's Gap is one of the strangest features of the entire tetrapod record. It sits directly after the most dramatic structural transition of vertebrate evolution, the move from fin to limb, from water to land, and it obscures exactly the period during which the consequences of that transition should have been unfolding. What were the tetrapods doing during the first 15 million years of the Carboniferous? Were they radiating onto dry land in large numbers, or were they still predominantly aquatic, as their Devonian predecessors appear to have been? What was the shape of the early terrestrial ecosystem they entered? Which of the many polydactylous forms of the late Devonian had survived the Hagenberg event and which had not? These questions are all obscured by the silence. The silence is not a narrative convenience. It is a real absence of rock-preserved bodies across a critical stretch of geological time, which has made the earliest stages of truly terrestrial vertebrate life harder to reconstruct than almost any other major transition in animal evolution. What is clear from the far side of the gap is what the tetrapods looked like when the record resumes. By about 345 million years ago, in the early Carboniferous, a diverse assemblage of tetrapods begins to appear in fossil localities from Scotland, North America, and elsewhere. These animals are different from the Devonian forms. Their limbs are more robust, their rib cages are stronger, their bodies are better suited to bearing weight out of water. Some of them still retain clear aquatic features, but many are recognizably terrestrial in posture and proportion, and within a few more million years, the lineage gives rise to the amphibians and to the earliest amniotes, the ancestors of all reptiles, birds, and mammals alive today. Whatever happened inside Romer's Gap, the tetrapod lineage came out of it fundamentally changed. The Devonian experiments with high-digit counts were, by this point, over. The 5-digit pattern, pentadactyly, had become the standard. It would stay that way, with minor variations, for the next 345 million years. There has been a long argument about why the digit count stabilized at 5, and the honest answer is that we do not fully know. Several hypotheses are on the table, and they are not mutually exclusive. One is developmental, that the Hox gene network patterning the distal limb is, for deep mechanistic reasons, most stable when it produces 5 discrete digits, and that other counts are harder to maintain developmentally without cascading into defects that reduce survival. Another is historical, that the lineages with 5 digits happen to be the ones that survived Romer's Gap in significant numbers, and that everything downstream of that bottleneck inherited their count simply because its carriers were the ones left. A third is functional, that a 5-digit limb for the particular size range and locomotor repertoire of early Carboniferous tetrapods may have offered a workable compromise between dexterity, weight distribution, and limb strength. The truth is probably some combination of all three, weighted differently in different branches. But it is worth being clear that 5 is not, in any cosmic sense, the correct number of digits for a vertebrate. It is the number that got through. The animals that were lost in the end Devonian extinction did not fail because their bodies were inferior. Acanthostega was not a failed attempt at a tetrapod that got the digit count wrong. Acanthostega was a successful Devonian tetrapod that lived well in the ecosystem it inhabited and then died, along with much of that ecosystem, in a climatic and atmospheric event that had nothing to do with its 8 fingers. The extinction was not a quality filter. It was a bottleneck, which means that what came through was not chosen for its superiority, but simply for its presence on the right side of a geological disaster. The sharpness of this distinction matters. Selection, operating over millions of generations inside an ecosystem, gradually tunes bodies to the demands of that ecosystem. Extinction, operating in geologically compressed intervals of global stress, prunes lineages without reference to the fine-scale adjustments that selection has made. When selection and extinction run on different timescales, as they always do, the lineages that come through an extinction are not necessarily the lineages that were the best adapted to the pre-extinction world. They are the lineages that happen to be elsewhere, or elsewhen, or underground, or at the margins when the world changed. This is an aspect of evolutionary history that popular accounts tend to underweight. The story of the transition from fish to tetrapod, as it is usually narrated, runs as if each stage is an improvement on the last, culminating in a modern form that represents the most refined version of the lineage. The record does not support that reading. The record supports a much stranger reading, in which successful, well-adapted animals are routinely eliminated by events indifferent to their adaptations, and the survivors of those events go on to found everything that comes afterward, regardless of whether they were the best examples of their own time. The dominant vertebrate lineages of the Devonian did not, for the most part, survive into the Carboniferous. The placoderms were gone. Most of the lobe-finned fish lineages were gone. Only a small residue of sarcopterygians remained, the lineage that became the lungfish, the lineage that became the coelacanths, and the lineage that had become the tetrapods. Everything that has happened in vertebrate evolution since, including the fact of you listening to this sentence, descends from that narrow survival. There is a specific feature in your own body that carries the memory of the 5-digit settlement that came out of Romer's Gap, and it is probably not what you would guess. It is not in your hand at all. It is in your wrist. If you run your fingers along the bumps and hollows of your wrist bones, you can feel a cluster of roughly 8 small elements arranged in 2 rows, which together allow the remarkable range of motion that your hand has at its base. The specific architecture of those wrist bones, the number of them, the arrangement of their articulations, the way they permit the hand to tilt, rotate, and flex, was established in the early Carboniferous, in the first wave of tetrapods that emerged from the gap. Every tetrapod wrist, from the forefoot of a frog to the forelimb of a horse, to the wing of a bat, to the flipper of a whale, is a variation on that early Carboniferous plan. The plan was set not by any organism's need, but by what the surviving lineages happened to have when the gap closed. Whatever subtler versions may have existed in the Devonian, in Acanthostega, Ichthyostega, or the many animals we do not yet have, went into the silence with the rest of the lost tetrapods and were not available to the forms that remained. The thing to hold on to, when the story leaves the Devonian and enters the long continuity of everything that followed, is that the transition from fish to tetrapod was not completed in the Devonian at all. The bodies had started to change. The pieces were being reassembled. But the actual establishment of a stable, ground-dwelling, lineage-defining tetrapod form happened on the far side of a geological crisis that killed most of the animals that had been working on the problem. The tetrapods that walk the earth today are not the refined descendants of the Devonian pioneers. They are the refined descendants of whatever lineages among those pioneers happened to survive a catastrophe that did not care about pioneering. What they carried forward was a workable version of the tetrapod body. What they lost, the high-digit forms, the alternative limb patterns, the body plans we will never see because they were not preserved in Carboniferous rocks, is invisible now and will remain invisible, and is nevertheless part of the shape of the story. The silence matters. The animals who went into the silence carried things with them that we cannot recover. What we have is what came out. What came out of the silence, roughly 345 million years ago, was a tetrapod body stable enough to persist. It had 4 limbs, each ending in 5 digits. It had a rib cage that could support a body against gravity. It had a neck that could turn independently of the shoulders. It had a lung that took over from gills as the primary breathing organ, connected to the mouth through a shared passage whose geometry it had inherited from its fish ancestors and never rebuilt. It had a jaw rebuilt from different bones than its reptilian synapsid descendants would use, and inside its ear, the early outlines of a vibration transmission system that would eventually be remade from the retired bones of that jaw. It had a hand whose underlying genetic program had been written in the form of regulatory sequences and Hox gene deployments long before there were hands anywhere in the world. It was a body whose pieces were, almost without exception, older than the animal carrying them. What that body did over the next 345 million years was diversify. The same basic plan, 4 limbs, 5 digits per limb, a neck, a single pair of lungs, an inherited throat, was elaborated into nearly every vertebrate form that has walked, run, crawled, climbed, burrowed, swum, or flown on Earth. Salamanders kept the general layout, slightly modified. Frogs compressed the tail and extended the hind limbs into something adapted for jumping. Reptiles scaled up the rib cage, reoriented the hip, and eventually split into the lineages that would become turtles, snakes, lizards, crocodiles, and dinosaurs. The dinosaurs, in turn, elaborated some of their branches into birds, whose wings are modified forelimbs in which the wrist and digits have been rearranged but not lost. Mammals took the same plan and built it into shapes that no Devonian tetrapod would have recognized as related to itself: the long limbs of a horse, the wing hand of a bat, the fused digits of a hoof, the flipper of a whale, the grasping hand of a primate, your own arm. Every one of these is the same body, altered. Nothing new has been built from scratch. The humerus radius ulnar wrist digit architecture that was assembled piece by piece across the Devonian is the architecture your forelimb is still running on today. This is the outline of the thread, and it is worth saying plainly because the thread is what this kind of story is ultimately about. Every ancestor you have ever had, without exception, lived long enough to reproduce. This is not remarkable, this is the only possible history, because any ancestor who failed to reproduce is, by definition, not an ancestor. Every one of the 375 million years of your lineage since the shallow Devonian rivers has been filled by organisms: fish, then stem tetrapods, then amphibians, then reptiles, then mammal-like reptiles, then small nocturnal mammals, then primates, then a particular lineage of African primates, each of whom happened to survive long enough, under whatever conditions they faced, to pass their body on. The chain has never broken. Not once. If it had broken at any point, by any margin, even for a single generation, in any of the hundreds of millions of years it has been running, you would not be in a position to hear this sentence because there would be no you. The existence of your body, right now, on this particular evening, is evidence of an unbroken sequence of animal survivals so long that the human imagination is not well equipped to encompass it. The existence of anyone's body, right now, is such evidence. The thread is common to every living thing on Earth. Each of us is at its current end. That is the philosophical moment this kind of story builds toward, and it is worth sitting with for a few sentences, because what it is actually saying is stranger than it sounds. The fact that you exist is, in one sense, ordinary. You are a product of the same biological processes that produced every other organism, and nothing about your existence is more miraculous than the existence of a snail or a pine tree. In another sense, your existence is the end of a specific line of inheritance whose terms were not negotiable. The animal in the Devonian river, the fish whose fin already contained the rough outline of your hand, did not know anything about you. The mammal-like reptile with two jaw joints, slowly ceding the old one to the purpose of hearing, did not know anything about you either. The small, nocturnal mammal that survived the asteroid impact 66 million years ago and whose lineage happened to be one of the few that came through the end Cretaceous extinction intact, did not know anything about you. Your existence was never their concern. Their existence was their concern, and they lived it well enough and long enough, and then they died, and something descended from them continued to live, and eventually one of those descendants was you. You are what they did without knowing they were doing it, and you, in turn, are doing whatever you are doing now without knowing what will be done with it, and none of that knowledge is required for the process to continue. This is not a reassurance. It is not a form of comfort, in the sense that ordinary comforts operate. What it is, if it is anything, is a perspective. The universe has not been arranged for anything. The process that produced you has no orientation toward your well-being, or your continuation, or your understanding of itself. It is a process that has simply been running for as long as there has been life to run it, and it will continue to run for as long as some lineage, somewhere, is still reproducing. What you do with it is yours. The process does not need you to do anything. The process will, in time, produce other animals in other configurations from whatever portion of the lineage persists past you. Some of those animals may look quite different from you. Some of them may not exist as terrestrial forms at all. None of that is decided. What is decided is that you are, right now, one of the points at which the thread is still being held. If you want to feel the thread in your own body one more time before the story ends, do the following. Place your hand, palm down, somewhere flat, on your chest, on your thigh, on the mattress beside you, wherever it is comfortable. Feel the weight of it. That hand contains, inside it, a humerus radius ulnar arrangement that was present in Eusthenopteron, a wrist architecture that was established in the early Carboniferous, 5 digits whose count was settled at Romer's Gap, a set of small tendons whose patterns trace back to brachiating primates, and a skin whose sensitivity was refined across tens of millions of years of mammalian life in environments that selected for fine tactile discrimination. Every centimeter of the hand has a history. Every bone has a history. Every nerve has a history. The hand resting now against whatever it is resting against is not yours in any recent sense. It is the current form of something much older, and you are its current operator, and when you are done with it, the shape will be passed, in modified form, into whatever lineage continues from yours. Breathe in. Feel the air enter through your mouth, through the shared passage that has been shared since the Devonian, past the epiglottis that tips forward each time you swallow, down into the lung that was a fish's lung before it was yours. The lung inflates. The diaphragm, which is a mammalian innovation, a sheet of muscle that early synapsids elaborated from a more modest arrangement in the body wall, pulls downward, expanding the chest cavity. Oxygen crosses into your blood, carried by hemoglobin, a protein whose origin traces back past fish to the oxygen transport molecules of much earlier animals. The blood moves through a 4-chambered heart whose basic architecture was established in the amniotic ancestors of reptiles and mammals, and whose rhythm is maintained by a pacemaker tissue whose cells have been doing the same job, in nearly the same way, since the first chordates in the Cambrian. All of this is happening now, inside you, while you listen. None of it was designed for the evening you are spending. All of it is happening regardless, because the machinery is still running. The thread continues. It runs through your body, right now, in every heartbeat and every breath and every small movement of your hand. It runs through the body of every other living thing on Earth. in the same way. It has never once stopped. It has survived 5 mass extinctions. It has survived the Hangenberg event, the end Permian collapse, the end Cretaceous impact, and a long series of smaller bottlenecks that nearly ended it and did not. It is running at this moment in ways that will someday be invisible to anyone, because no one will be left to watch them. It will still run. If you are lying down, you can let your body relax a little further. Your jaw can soften. Your shoulders can fall. The hand that was resting a moment ago does not need to hold any particular shape. Your breath is slowing on its own. You do not need to pay attention to any of this. The fish in the Devonian River, holding itself against the current 375 million years ago, did not know it was your ancestor. It was waiting for a shadow at the surface. It did not know it would be you, eventually, in a different body, in a different kind of evening, listening to a voice describe the shape of the inheritance it had left behind. It did not know anything. It was simply a living thing, in its own time, doing what its kind did. And now, in your time, you are a living thing, doing what your kind does. One of the things your kind does is sleep. The thread does not require your attention tonight. It will continue without you for the next several hours. You can let go of it. Rest now. The water is still there, and the river is still there, and the hand is still there, and the animals that went before you are all still there, held in the body you are lying down in. Good night.